Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the radius of this circle that is described by the right triangle ABC. In the second question, we'll find out the area of the low right triangle BCD that is described by this quarter circle. So we start with the first question. In the drawing, we have the right triangle ABC. Side AB equals to 8 units. And we also know that the length of side BC and the length of the hypotenuse AC are integer numbers. And we know that angle ABC equals to 90 degrees. And we want to find out the radius of this circle that is described by the right triangle ABC. So first of all, we will define side BC of triangle ABC as A. That is to say, the length of side BC is A units, and we define the length of the hypotenuse AC as B. Okay, so the hypotenuse AC, it is equal to B units according to our definition. And we will implement the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem, in the right triangle ABC, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC squared. It is equal to the sum of the squares of the perpendiculars, that is to say, it is equal to BC squared plus AB squared. So in the right triangle ABC, here by PT is a relation for Pythagoras theorem. So AC squared plus BC squared plus AB squared. According to what is given us in the question, A B equals to 8, so AB squared is A squared, that is 64. So if AC equals to B, so AC squared is B squared. That is equal to BC squared. BC is A, so BC squared is A squared plus AB squared, that is 8 squared. A squared is 64. In conclusion, we found out that according to equation number 1, b squared equals to a squared plus 64. We subtract a squared from this equation number 1, and we get it according to equation number 1, b squared minus a squared equals to 64. We use the algebraic identity that b squared equals to b squared minus a squared equals to b plus a times b minus a. So b squared minus a squared equals to b plus a times b minus a, that is equal to 64. Okay. So according to question number 1, b plus a times b minus a equals to 64. So here we know that according to what is given in the question, AC and BC are integers, okay, AC and BC are integers. According to our definition, AC is A and AC is B and BC is A, so A and B are integers. So, and we also know that A and B are the lengths of the right triangle ABC. So A and B as a length, they must be a positive numbers. They are lengths, and therefore they must be a positive number. So we have two things here. We know that AB are integers and AB also positive numbers. So from those two things we can write down that A and B are positive integers. A and B are positive integers. And because of the fact that A and B they are positive integers, we can say that we can write down that A plus B or B plus A must be greater than B minus A, because when you add two positive integers to each other, they will be always greater, and then the two integers that you subtract them by each other. Okay, so b plus a is greater than b minus a, and we also know, so b plus a, they are positive integers, and here b is the hypotenuse, and the hypotenuse is always greater than the perpendicular. So we know that b is greater than a, so if we subtract a from this inequality, we get that b minus a is greater than 0. So b minus a is greater than 0, that is to say b minus a will be also a positive integer. B minus a, it is also a positive integer, because it is a positive, and when you subtract two positive integers from each other, and you know that one is greater than the other one, then the result must be a positive integer. B is greater than a, so b minus a will be also a positive integer. So actually, according to equation number 1, we know that b plus a times b minus a equals to 64. So actually, according to equation number 1, when we multiply two positive integers by each other, the result is 64. So which positive integers we have that when we multiply them by each other will give us the result of 64. Actually, the possibilities are not too much. We will write down all the possibilities that we have, that the multiplication of two positive integers will give us the result of 64. Okay, so here we have so the first positive integer could be 1, and the second positive integer could be 64, and the multiplication of those two numbers will give us 64. Then we have also the option that the first positive integer is 2, and the second positive integer is 32, and the multiplication of the two positive integers will give us 64. 2 times 32 is 64. Then we also have the option that the first positive integer is 4, and the second positive integer is 16, and 4 times 16 will give us 64. And we also have here the option that the first integer the first positive integer is 8 and the second positive integer is also 8. And the multiplication of 8 times 8 is 64. And we also have the option that the first integer is 16 and the second integer is 4, and 16 times 4 is 32. Then we have also the option that the first integer is 32 and and 32 times 2 will give us 64, and finally we have the option that the first integer is 64 and the second positive integer is 1, and 64 times 1 will give us 64. Okay, but here we've already found out that b plus a must be greater than b minus a. So we know that 1, that is b plus a, is smaller than 64, so this option is invalid option. We cancel this possibility. 2 is also less, 2 that is b plus a is less than 32 that is b minus a, so this option is invalid option. We cancel this option. And we have also 4 times 16. 4 is less than 16, so we cancel this option, and 8 is equals to 8, that is to say 8 is not greater than 8, so we cancel this solution. 16 that is b plus a is greater than 4 that is b minus a, so this option is valid option. 32 is greater than 2, so this option is valid option. And 64 is greater than 1, so this is a valid option. Okay. In the next step, we will add the two numbers together in order to find out what is the result that we will get here. So if we add b plus a to b minus a, we'll get that b plus a plus b minus a. So b plus b is 2b and a minus a is 0. So in conclusion, I found out that if we add the two numbers together, we must get 2b that is an even number. 2b is even number because of the fact that b is a positive integer. 2b must be an even number. That is to say, when we add those two numbers together, we must get an even number. So we check which numbers here are even numbers. 16 plus 4 is 20, and 20 is even number, so this option is a valid option. 32 plus 2 is 34. 34 is an even number. And this 64 plus 1 is 65. And 65 is an odd number, is not an even number, so this option is invalid option. So we left only with two possibilities for a and for b plus a and b minus a. The first option is that b plus a is 16 and b minus a is 4, and the second option is that b plus a is 32 and b minus a is 2. So I write the two options here together. Here I found out that according to the first option, b plus a equals to 16, while b minus a equals to 4. So this is the first solution that is possible for b plus a and b minus a, and the second solution that is possible is that b plus a is equal to 32, while b minus a equals to 2. Okay, so here we will add the two equations together. B plus b is 2b, and a minus a is 0, so 2b equals to 16 plus 4, that is 20. So if I know that according to the first solution 2b equals to 20, we divide this equation by 2, and we'll get that b equals to 20 over 2 is 10. So b equals to 10 units according to the first solution, and we know that b plus a equals to 16. Here we subtract b from this equation, and we get that a equals to 16 minus b. A equals to 16 minus b, but we have already found out that b equals to 10. So we can write here that a equals to 16 minus 10, that is 6. So in conclusion, we found out that according to the first solution, a, that is the perpendicular of the right triangle ABC, it equals to 6 units, and the hypotenuse of the right triangle ABC, that is B, it is equal to 10 units. That is according to the first solution for A and B, and according to the second solution, b plus a is 32 and b minus a is 2. We will add the two equations together, and we get that b plus b is 2b, and 2b equals to 32 plus 2 is 34. 2b equals to 34, we divide this equation by 2, and we get that b equals to 34 over 2 is 17, so the hypotenuse b equals to 17 units. Here we have the equation that b plus a equals to 32. b plus a equals to 32. We'll subtract b from this equation, and we'll get that a equals to 32 minus b. That is to say, a equals to 32 and b is 17. 32 minus 17. So a equals to 32 minus 17, that is 15. So in conclusion, according to the second solution, we found out that a equals to 15 units, and the hypotenuse b equals to 17 units. So we have here two solutions that are possible for A and B. We will draw the two solutions here. According to the first solution, A equals to 6 units and B, the hypotenuse B equals to 10 units. So here we already know that here side AB equals to 8 units. This is a right triangle, and we found out that side BC equals to 6 units, and the hypotenuse AC equals to 10 units. And inside this triangle ABC, according to what is given us in the question, we have this circle that is inscribed by triangle ABC, and we are looking for the radius of this circle that is inscribed by triangle ABC. Okay, so we actually found out the length of the sides of the triangle, that is 8, 6, and 10, the length of the sides of the right triangle. And now we have to find out the radius of this circle that is inscribed by the right triangle, triangle ABC. And the second option that we have here is that side AB equals to 8 units. It is given as the question. Okay, AB equals to 8 units. And BC side BC, that is actually A, according to the second solution, it is equal to 15 units. And the hypotenuse AC equals to 17 units. And inside this right triangle, triangle ABC, we have this circle that is inscribed by triangle ABC, and we are looking for the radius, to find out the radius of this circle that is inscribed by the right triangle, triangle ABC, and we already found out that the hypotenuse AB equals to 8 units, according to what is given in the question. The hypotenuse, the perpendicular AB equals to 8 units, the perpendicular BC equals to 15 units, and the hypotenuse of this right triangle, triangle ABC equals to 17 units. And we want to find out the radius of this circle that is inscribed by triangle ABC. So we have two options for the solution for the radius of the right triangle and for the radius of the circle that is inscribed by the right triangle, triangle ABC. So in order to find out the radius of this circle that is inscribed by triangle ABC, here we'll take triangle ABC. This is triangle ABC that could be any triangle. We'll define side AB. So inside this triangle, triangle ABC, we have this circle that is inscribed by the triangle ABC, and we want to find out the radius of this circle that is inscribed by triangle ABC. So we'll find out the radius of this circle in triangle ABC, that could be any triangle, and then we'll use the formula in order to find out the radii of the circles in our specific right triangles. So we'll define side AB as A, side AB equals to A according to our definition. We'll define side BC as B. Here side BC equals to B according to our definition. And side AC equals to C according to our definition. Okay, so this is triangle ABC that could be any triangle. and we'll find out the radius of this circle that is described by triangle ABC, and then we will use the formula for the radius that is described by this circle in our specific two right triangles that we know the lengths of the sides of the right triangles. So here we have triangle ABC that could be any triangle, and we have this circle with the radius R, and we know that side BC is tangent to this circle at point N. So we define the point of tendency of side AB with this circle as M. We will define the center of this circle as O. We will join points O and M together by a straight line. I repeat again that triangle ABC is a right triangle, but it could be any triangle. And inside the right triangle, triangle ABC, we have this circle that its radius is R. And we want to find out the value of R in the general triangle, triangle ABC, that would be any right triangle, and then we will use the formula for the radius, and we will find out the radii of our specific right triangles. So here we have point O is the center of the circle, point M is the point of the circle itself. This is exactly the definition of a radius. That is to say, OM is the radius of this circle that is equal to capital R. Okay? So, and we have here rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then according to rule number 1, tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, here we have the radius ON that is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then according to rule number 1, tangent BC will be perpendicular to the radius NO. So if BC is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay, so we actually found out that in quadrilateral NOBM, this quadrilateral, we have 1, 2, 3 right angles. And we know that the sum of the angles in any quadrilateral is equal to 360 degrees. And the sum of 3 right angles is 90 times 3 is 270 degrees. So 270 degrees plus the size of the fourth angle, that is actually angle MON, in total it must be equal to 360 degrees. That is to say, this angle must be also equal to 90 degrees in order to complete the sum of the angles in quadrilateral MOBN to 360 degrees. This angle must be equal to 90 degrees. So we actually found out that in quadrilateral MOBN we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral MOBN is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, MO equals to BN. So we know that MO equals to BN, but we know also that MO equals to R. So MO equals to BN and MO also equals to R. Therefore, we derive from this that Bn is also equals to R. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we get that ON equals to MB, or N equals to MB. But we know that ON equals to R. So from one side ON equals to MB, and from the other side ON equals to R. Therefore, MB also must be equal to R. So we actually found out that the quadrilateral MOBN, it is not a rectangle but a square, because all of its sides are equal to each other. Okay, so here, what is the length of side AM? From the drawing it is very easy to see that AM equals to AB minus MB. Again, AB minus MB equals to AM. That is to say, AM equals to AB, that is A, minus MB, that is R. So in conclusion, we found out that AM equals to A minus R. Here we find out the length of line segment NC. What is the length of line segment NC? It is very easy to see from the drawing that NC equals to BC minus BN. Again, BC minus BN equals to NC. That is to say, NC equals to BC, that is B, minus BN, that is R. So in conclusion, we found out that NC equals to B minus R, and AM equals to A minus R. And we also have rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. Here we define the point of tangency of tangent AC with this circle as Z. I repeat on rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. So if we focus on the common standpoint point A, from the common standpoint point A, we have two tangents to this circle. We have tangent AM and tangent AZ, and according to rule number 2, they are equal to each other. That is to say, AM equals to AZ. AM equals to AZ, but we have already found out that AM equals to A minus R, therefore AZ must be also equal to A minus R. So AZ equals to A minus R. Likewise, if you focus on the common standpoint point C, from the common standpoint point C, we have two tangents to this circle. We have tangent CZ and tangent CN. Okay? And according to rule number 2, they are equal to each other. That is to say, CN equals to CZ, according to rule number 2. But we have already found out that CN equals to B minus R. Cn equals to B minus R, therefore Cz must be also equal to B minus R because they are equal to each other. So in conclusion, we found out that AZ equals to A minus R and ZC equals to B minus R. And according to our definition, the hypotenuse AC, it is equal to C units. Here we actually define side AB as A, we define side BC as B, we define side AC as C. Okay, so AC equals to C according to our definition. So what is the length? Of AC, the hypotenuse AC? The length of the hypotenuse AC from the drawing is very easy to see. That AC, here AC equals to the hypotenuse AC equals to AZ plus ZC. AZ plus ZC. I'll repeat again, the hypotenuse AC in the domain equals to AZ plus ZC. AC equals to AZ plus ZC. According to our definition, the hypotenuse AC is equal to C. The hypotenuse AC equals to C, so we substitute AC by C. And C equals to AZ. AZ is A minus R, so we substitute AZ by A minus R plus ZC. We already found out that ZC equals to B minus R, so we substitute ZC by B minus R. So in conclusion, we found out that the hypotenuse AC of the right triangle, triangle ABC, that could be any triangle, it is equals to C equals to A minus R plus B minus R, that is to say it is equal to A plus B, minus R plus minus R is minus 2R. The hypotenuse C equals to A plus B minus 2R. We will add 2R to this equation, and we will get that 2R plus C equals to A plus B. Here we will subtract C from this equation, and we will get that 2R equals to A plus B minus C. 2R equals to A plus B minus C. Here we divide this equation by 2, and we'll get that R, the radius that we are looking for, the radius of this circle that is inscribed by triangle ABC, equals to A plus B minus C over 2. Okay? So, in this way we found out the radius of any circle that is inscribed by triangle ABC that could be any triangle. The radius of this circle will be equal to the sum of its perpendiculars, the sum of the perpendiculars of the triangle, the right triangle ABC, minus the hypotenuse that is C over 2. So we will implement the new formula in our specific right triangles that we found out in our specific question. Here we actually found out that there is two possibilities for two right triangles that could be the answer to our questions. And we have here, we have the radius of any circle that is inscribed by a right triangle, triangle ABC. That radius equals to A plus B, that is the sum of the perpendiculars of the right triangle, the sum of the perpendiculars of the right triangle, minus C, that is the hypotenuse, over 2. Okay, so here, so we'll implement the new formula in our two triangles. According to the new formula, R equals to A plus B minus C over 2. Here the radius of this circle that is inscribed by this right triangle, triangle ABC, will be equal to A plus B, that is the sum of its perpendiculars, that is 8 plus 6, minus the hypotenuse, that is 10, over 2. So 8 plus 6 is 14, and 14 minus 10 is 4, and 4 over 2 is 2. So the first solution for the radius that is inscribed by the right triangle ABC could be that the radius, the length of the radius, is equal to 2 units. And the second solution for the radius is that R equals to A plus B, that is 8 plus 15, minus the hypotenuse, that is 17 over 2. 8 plus 15 is 23, and 23 minus 17 is 6. So it is 6 over 2, that is 3 units. Okay, so we actually found out two answers to our question. The first answer is that the radius of the circle that is inscribed by the right triangle ABC is equal to either 2 units, or the second option, that the radius equals to 3 units. Okay, and that is the answer to the question. Okay, the radius here, the radius of this circle that is inscribed by right triangle ABC could be equal to either 2 units, or it could be equal to 3 units. Okay, so we finished with the first question. In the next step, I present to you the second question, and we will solve the second question in 2 different methods. Okay. In the second question, we have a quarter circle. AOB is a quarter circle. We know that side OB equals to 2 units. And we also know that AD equals to DO. Inside this quarter circle, there is a right triangle that is inscribed by the quarter circle, the right triangle DCB. Angle DCB equals to 90 degrees, and we want to find out the area of this right blue triangle DCB. So we start with the first method. We actually know that AOB is a quarter circle, therefore O must be the center of the quarter circle, and angle AOB must be equal to 90 degrees. And OB must be the radius of the quarter circle, and AO must be also equal to the radius of the quarter circle. So we can write here that AO must be equal to OB. AO must be equal to OB, and both of them are the radii of the quarter circle, and it is given as a question that the radius of the quarter circle equals to 2 units. So here AO equals to OB equals to 2. But we know that AO equals to AD plus DO. So we can write down that AO equals to AD plus DO. We define AD as X. If AD equals to X, then DO also equals to X, because they are equal to each other. So we get that X plus X equals to AO, that is equal to 2 units. X plus X is 2X, and 2X equals to 2. We divide this equation by 2, and we get that X equals to 1 unit. So AD that is equal to X, it is equal to 1 unit, and DO that is also equal to X, it is also equal to 1 unit. Okay? So in the next step, we'll complete the quarter circle to a circle. So we completed the quarter circle to a circle, and we'll extend the radius BO until it touches the circle in this point. We'll define the touching point of the extended BO and the circle is point P. Here point O is the center of the circle, point P is the point of the circle itself. So PO is the radius of the circle. That is to say, PO is the radius of this circle that is equal to 2 units, because the radius of the circle is the same as the radius of the quarter circle. They have the same radii. So here we extended the radius BO by straight line. BO as a radius is a straight line, and when you extend a straight line by a straight line, the result must be a straight line. So PB is a straight line, and we know that the sum of the angles on one side of a straight line is equal to 180 degrees. So if you focus on the upper side of the straight line PB at point O, the sum of the angles must be equal to 180 degrees here. Which angles we have in the upper side of PB at point O? We have here 90 degrees, plus this angle AOP. So 90 degrees plus angle AOP, in total they must be equal to 180 degrees. So that is to say, this angle must be equal to 90 degrees in order to complete the sum of the angles, and the upper side of the straight line BP to 180 degrees, this angle must be equal to 90 degrees. So here, chord BP passes through point O, that is the center of the circle. Therefore, chord PB is the diameter of the circle. PB is the diameter of the circle. Okay. In the next step, we'll extend side CD until it touches the circle. Repeat again. We'll extend side CD until it touches the circle. Suppose that we don't know where is the touching point. So suppose that the touching point is at point X. Therefore, we actually created here angle BCX. Angle BCX, that is definitely a peripheral angle. Repeat again, angle BCX is a peripheral angle because it touches the circle on both sides, and the vertex of the circle is at point C. Therefore, BCX is defined as peripheral angle. But we also know another thing about the peripheral angle BCX. BCX, that is equal to 90 degrees. It is given us the question. So peripheral angle BCX equals to 90 degrees according to what is given us the question. But we also know that any peripheral angle that is equal to 90 degrees must rest on the diameter of a circle. That is to say, peripheral angle BCX must pass through point P because it must rest on BP, that is the diameter of the circle. That is to say, peripheral angle BCX must be equal to peripheral angle BCP. Why? Because any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle, that is PB. So in order that peripheral angle BCX will rest on the diameter, it must touch point P. So when you extend the side CD by a straight line, it must pass through point P. Because peripheral angle BCX must rest on PB, that is the diameter of the circle. That is to say, peripheral angle BCX, actually it must equal to peripheral angle BCP, and they are both equal to 90 degrees because any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle, that is PB. Therefore, peripheral angle BCX equals to peripheral angle BCP, and they are both equal to 90 degrees. In this way, we proved that the peripheral angle that we created here, that is BCX, is actually equals to peripheral angle BCP because it must rest on the diameter BP. Okay? So here we have here a right triangle PDO. In the right triangle PDO, we will implement the Pythagoras theorem. So by PT is abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. So PO square plus DO square must be equal to the square of the hypotenuse, that is PD square. Okay? So according to the Pythagoras theorem, on the right triangle PDO, PD square plus DO square must be equal to PO square plus DO square must be equal to PD square. PO equals to 2, so PO square is 2 squared, that is 4, plus DO square. DO equals to 1, so DO square is 1 squared, that is 1, that is equal to PD square. So in conclusion, we found out that 4 plus 1 equals to PD square, 4 plus 1 is 5, so 5 equals to PD square. We take out all of this equation and we get that PD equals to the square root of 5 units. PD equals to square root of 5 units. So we can write here that PD equals to the square root of 5 units. In the next step, we'll implement the Pythagoras theorem on the right triangle DBO. On the right triangle DBO, according to the Pythagoras theorem, by PT we get that DO square plus OB square equals to DB square, that is the square of the hypotenuse. So in the right triangle DBO, DO square plus OB square equals to dB square. DO equals to 1, so DO square is 1 squared, that is 1, plus OB square. OB equals to 2, so OB square is 2 squared, that is 4. That is equal to dB square. So in conclusion, if we know that 1 plus 4 equals to B square, to dB square, 1 plus 4 is 5, so 5 equals to dB square. We take a root out of this equation, and we get that dB equals to the square root of 5 units. dB equals to the square root of 5 units, so I can write here that dB equals to the square root of 5 units. In the next step, we will extend the radius AO by a straight line until it touches the circle. At this point, we will define the touching point of the extended AO, and the circle is point Z. O is the center of the circle. Z is the point of the circle itself, that is to say, OZ is the radius of the circle, that is equal to 2 units. So in the next step, I will present to you a rule that is related to two chords that intersect with each other inside the circle, and we will implement the new rule, the rule that is not a new rule in our drawing. I've already mentioned this rule a couple of times, so I'll repeat on it shortly. We have here this circle, and inside this circle we have two chords that intersect with each other. Here we have chord AB. This is chord AB. I repeat again, this is chord AB that intersects with chord CD. This is chord CD, and the intersection point of chord AB with chord CD is at point O. So if this is the data that has been given to us, that chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Okay? Again, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We actually can implement rule number 1 in our drawing, because in our drawing we have chord AZ. This is chord AZ that intersects with chord CP at point D. Again, chord AZ intersects with chord CP at point D. Therefore, so write it down. In our drawing, chord AZ intersects with chord CP is point D. Point D is the intersection point of chord AZ with chord CP. Therefore, so repeat again, in our drawing, chord AZ intersects with chord CP at point D. Therefore, according to rule number 1, we get that AD times DZ, AD times DZ will be equal to PD times DC. I'll repeat again. Moving to rule number 1, AD times DZ equals to PD times DC. So AD is 1, DZ is 1 plus 2, that is 3, and it is equal to PD. PD is square root of 5 units, and DC is the missing 9 segment. So in conclusion, I found out that according to rule number 1, 3 equals to 5 times square root of 5 times DC. We divide this equation by square root of 5 and we get that DC, the missing 9 segment, equals to 3 over square root of 5 units. So I found out that DC equals to 3 over square root of 5 units. We write here that DC equals to 3 over square root of 5 units. In the next step, we will implement the Pythagoras theorem on the right blue triangle, triangle DCB. This is the triangle that we are looking for. We want to find out the area of this right blue triangle. So, according to the Pythagoras theorem on the right blue triangle, triangle DCB, by PT is the equation for Pythagoras theorem. We get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is dB, therefore the square of the hypotenuse is dB squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to DC squared plus CB squared. Okay? So according to the Pythagoras theorem, dB squared equals to DC squared plus CB squared. dB is square root of 5, so dB squared is square root of 5 squared, that is 5. And it is equal to 3 to DC squared. DC is 3 over 5, 3 over square root of 5, so DC squared will be equal to 9 over 5 plus CB squared. So in conclusion, we found out that 5 equals to 9/5 plus CB squared. Here we subtract 9/5 from this equation and we will get that 5 minus 9/5 equals to CB squared. So here we will multiply 5 by 5 and then we will divide it by 5 in order to have a common factor with this expression. And we will get that 5 times 5 is 25, so we have here 25 minus 9 over 5 equals to CB squared. Twenty-five minus 9 is 16, so 16 over 5 equals to CB squared. Here we take a root out of this equation and we get that CB equals to the square root of 16, that is 4 over square root of 5. So in conclusion, we found out that CB equals to 4 over square root of 5 units. So you can write here that CB equals to 4 over square root of 5 units. Now it is very easy to find out the area of the blue right triangle, triangle DCB. The area of the blue triangle, triangle DCB, that is the area of the blue shape, equals to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. Okay, so here DC equals to 3 over square root of 5 times CB is 4 over square root of 5, all divided by 2. Okay, here in the numerator we have 3 times 4 is 12 over square root of 5 times square root of 5 is 5 over 2. 12 over 2 is 6. So in the numerator we have 6. In the denominator we left only with 5. So in conclusion, found out that the area of the blue right triangle DCB equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. Okay. I repeat again, according to the first method, we found out that the area of this blue right triangle DCB equals to either 6 over 5 square units, or in terms of numbers, it is equal to 1.2 square units. We finished with the first method. In the next step, I will present to you the second method. So we know that angle AOB equals to 90 degrees because we have here a quarter circle. We have already found out that AD, according to the first method, that AD equals to 1 unit. DO also equals to 1 unit. And here we will complete the quarter circle to a semicircle. We extended here the radius BO by a straight line. We define the touching point of the extended BO and the circle is point P. O is the center of the circle, of the semicircle. P is the point of the semicircle itself. Therefore, PO is the radius of this semicircle that is equal to 2 units, according to what is given us in the question. Here, we will extend side CD by a straight line until it touches the circle. So here, I have made on the same explanation. We extended the straight line CD until it touches the circle. So suppose it touches the circle not at point P, but at any other point that is point X. So created here peripheral angle BCX that is equal to 90 degrees according to what is given us the question. So peripheral angle BCX equals to 90 degrees. But we know that any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle. That is to say, peripheral angle BCX must touch point P. It must pass for point P. It must touch point P. Because any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle that is PB. Therefore, peripheral angle BCX must pass through point P. That is to say, peripheral angle BCX, it is equal to peripheral angle and only in this way we get that the peripheral angle BCX rests on PB, that is the diameter of the circle. Otherwise, if point P is not exactly if point X, it is not exactly at point P, then we will get that we have here a peripheral angle BCX that is equal to, actually, then it means that peripheral angle BCX cannot be equal to 90 degrees. Okay? Because here peripheral angle BCX that is equal to 90 degrees must pass through point B, because peripheral angle BCX that is equal to 90 degrees must rest on PB, that is the diameter of the circle. Therefore, peripheral angle BCX must pass through point P. That is to say, peripheral angle BCX equals to peripheral angle BCP. In this way, we will verify that the peripheral angle BCX equals to peripheral angle BCP, that is rest on the diameter of the circle. Okay? We have already found out that PD equals to square root of 5 units in the first method, or dB equals to square root of 5 units according to the first method. We have already found out in the first method that angle POD equals to 90 degrees. So in the right triangle DPO, we'll define angle DPO as theta. In the right triangle DPO, angle DPO equals to theta, angle DOP equals to 90 degrees. Therefore, this angle PDO, must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle, triangle POD 280 degrees. This angle must be equal to 90 degrees minus theta. And then we'll get that 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. So here, in the same way, we have the right big triangle, triangle PCB. This angle equals 90 degrees. This angle equals to theta. This angle equals to 90 degrees. So this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right big triangle, triangle PCB 280 degrees. This angle must be equal to 90 degrees minus theta. So in the next step, we will prove that the right triangle, triangle PDO is similar to the right big triangle, triangle PCB. So why those two right triangles are similar to each other? So the right triangle, triangle PDO is similar to the right big triangle, triangle BCB. So why those two right triangles are similar to each other? So first of all, we have those two angles that are both equal to 90 degrees, therefore they are equal to each other. Okay, so angle POD, this angle equals to angle PCB, this angle, and they are both equal to 90 degrees, therefore they are equal to each other. Repeat again. Angle POD equals to angle PCB equals to 90 degrees. In addition, this is a common angle that belongs to both triangles, so can I know that this angle equals to itself? So angle DPO equals to itself, that is angle CPB. That is equal to theta. It is a common angle that belongs to both triangles. And finally, we have those two angles that are both equal to 90 degrees minus theta, therefore they are equal to each other. So this angle that is actually angle PDO equals to this angle that is actually angle CBP, and they are both equal to 90 degrees minus theta, therefore they are equal to each other. So we actually prove that all three angles of triangle PDO can point to all three angles of triangle PCB, therefore triangle PDO is similar, this is the sign of similar, to triangle PCB, according to angle similarity rule. And from the fact that the two right triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that PD over PB equals to DO over CB, and it is equal to PO over PC. I repeat again, from the fact that the two right triangles are similar to each other, we will conclude that PD over PB equals to DO over CB equals to PO over PC. So here PD is square root of 5 units over PB. PB equals to 2 plus 2, that is 4. And it is equal to DO. DO equals to 1 unit over CB. CB is the missing 9/7, so we leave it as it is. And it is equal to PO. PO equals to 2 units over PC. PC equals to square root of 5 plus DC. So in conclusion, we found out that square root of 5 over 4 equals to 1 over CB, that is equal to 2 over square root of 5 plus DC. Okay, so here this is the first equation that we will create. The square root of 5 over 4 equals to 1 over CB. We will cross multiply this equation, equation number 1, and we'll get that square root of 5 times CB equals to 4. We'll divide this equation by square root of 5, and we'll get that CB equals to 4 over square root of 5 units. CB equals to 4 over square root of 5 units. So we can write here that CB equals to 4 over square root of 5 units. In the next step, we'll create the second equation from the wrong equation here. Here, the first column is equal to the third column. That is to say, square root of 5 over 4. Square root of 5 over 4 equals to 2 over square root of 5 plus DC. Okay, so this is the second equation that we added, that square root of 5 over 4 equals to 2 over square root of 5 plus DC. Here we cross multiply this equation, equation number 2, and we get that square root of 5 times square root of 5 plus DC equals to 2 times 4, that is 8. We'll open the brackets on this side of the equation number 2, and we get that according to equation number 2, square root of 5 times square root of 5 is 5, and plus square root of 5 times DC, that is equal to 8. Here we subtract 5 from this equation, equation number 2, and we get that according to equation number 2, square root of 5 times DC equals to 8 minus 5 is 3. We divide this equation by square root of 5, and we get that according to equation number 2, DC equals to 3 over square root of 5 units. So I found out that DC equals to 3 over square root of 5 units. Now it is very easy to find out the area of the blue right triangle, triangle DCP. The area of the right triangle, triangle DCB. The area of the right blue triangle, triangle DCB will be equal to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. Repeat again, and the area of the right blue triangle, triangle DCB equals to the base of the triangle, that is DC, times the height to the base, that is CB, over 2. So DC equals to 3 over square root of 5 units, CB equals to 4 over square root of 5 units, all divided by 2. Here, 3 times 4 in the numerator equals to 12. In the denominator we have square root of 5 times square root of 5 is 5, times 2. 12 over 2 is 6, so in the numerator we have 6, and in the denominator we left only with 5. So in conclusion, we found out that the area of the blue right triangle, triangle DCB equals to either 6 over 5 square units, or in terms of numbers it is equal to 1.2 square units. Okay, so actually we finished with the second method. In the next step I will summarize the lecture. We'll start with the first question, of course. In the first question, we have the right triangle, triangle ABC. Inside the right triangle, triangle ABC, we have a circle that is inscribed by triangle ABC. We know that side AB of the right triangle ABC equals to 8 units. And we want to find out the radius of this circle that is inscribed by triangle ABC. It is also given us the question that the length of side BC and the length of the hypotenuse AC, both of them are integers. Okay, and we want to find out the radius of this circle that is described by triangle ABC. So according to the Pythagoras theorem, So first of all, we define side BC as A and the hypotenuse AC as B. And according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to BC square plus AB square. So here AC equals to B according to our definition, so AC square is B square. BC equals to A according to our definition, therefore BC square is A square. And AB equals to A 8 units according to what is given as the question. So AB square is 8 squared, that is 64. So in conclusion, according to equation number 1, we found out that B square equals to A square plus 64. We subtracted A square from this equation number 1, and we found out that B square minus A square equals to 64. According to the algebraic identity, B square minus A square equals to B plus A times B minus A, so we substitute B square minus A square by B plus A times B minus A, and it is equal to 64 according to equation number 1. So it is given as the question that AC and BC are integers. But according to our definition, AC equals to B and BC equals to A. Therefore, A and B are integers. And we know that A and B are the lengths of the hypotenuse and the perpendicular of the right triangle ABC. So AB is lengths, it must be positive numbers. So from one side we know that AB, they are integers, and from the other side we also know that AB, they are also positive numbers. So from those two things we conclude that A and B are positive integers. Okay? A and B are positive integers. So if A is positive integer and B is positive integer, then A plus B must be also a positive integer. Therefore, the expression A plus B is a positive integer. We know that B is greater than A because B is the hypotenuse of the right triangle, and the hypotenuse is always greater than the perpendicular, so B is greater than A. B is greater than A, so if we subtract A from this inequality, we get that B minus A is greater than 0. B minus A is greater than 0. That is to say, B minus A is a positive integer. Why? Because we know that B minus A is a positive, and B and A are integers. And when you subtract B from A, when you subtract integer from other integer, and the result is a positive, so it must be a positive integer. Okay? So actually the expression B minus A is also a positive integer. So here you know that the expression B plus A is a positive integer, and the expression B minus A is also a positive integer. And we also know that if we multiply the first number by the second number, we get 64. So which positive integers we have that if we multiply one by each other, we get 64. There are few integers that will give us 64. There are few positive integers that will give us 64 when we multiply one by each other. So we will write down all the possibilities that we have here. The first number would be 1, and the second number could be 2, and 1 times 64 is 64. The first number could be 2, and the second number is 32, and 2 times 32 is 64. The first number is 4, and the second number is 16, and 4 times 16 is 64. The first number is 8, and the second number is also 8, and 8 times 8 is 64. The first number must be 16, and the second number must be 4, and 16 times 4 is 64. The first number is 32 and the second number is 2. And 32 times 2 is 64. The first number is 64 and the second number is 1. So 64 times 1 is 64. Okay, so here we know also that a and b are positive integers. Therefore, because of the fact that a and b are positive integers, when you add two positive integers, that is to say b plus a, it must be always greater than when you subtract them by each other. Okay, when you add two positive integers to each other, then the result must be greater than the possibility that you subtract one from each other. So b plus a, it must be greater than b minus a. That is to say, the first number that is b plus a must be greater than the second number that is b minus a. So which numbers we have here that are equal to b plus a that are greater than b minus a? Here 1 is smaller than 64, so it is not good because b plus a must be greater than b minus a, according to what we have already found out. So this possibility is incorrect possibility. 2 is smaller than 32, so it's not good. 4 is smaller than 16, it is not good. 8 is not greater than 8, so it is not good. 16 is greater than 4, that is a good option. And 32 is greater than 2, that is a good option. And 64 is also greater than 1, therefore it is a good possibility. But now we will add the first number to the second number in order to find out the result. So when we added the first number to the second number, that is to say b plus a plus b minus a, we got here that b plus b is 2b and a minus a is 0. b is a positive integer, therefore 2b must be an even number. So I actually found out that when we add the two numbers together, the result must be an even number. So we'll take only the possibilities that will give us an even number when we add the two numbers together. So here 16 plus 4 is 20, and 20 is an even number, so this possibility is a good possibility. 32 plus 2 is 34. 34 is an even number, therefore this possibility is a good possibility. But 64 plus 1 is 65. And 65 is odd number. It is not an even number. Therefore, this is not a good possibility because when you add the two numbers together, you must get an even number, and 65 is an odd number. So this is not a good possibility. So we left only with two solutions that are possible for b plus a and b minus a. The first solution that b plus a is 16 and b minus a is 4, and the second solution that b plus a is 32 and b minus a is 2. So we wrote down all the two possibilities. Here, according to the first solution, b plus a is 16 and b minus a is 4. So if we add the two equations together, we get that b plus b is 2b, a minus a is 0, and 16 plus 4 is 20. We divided, so we got the equation that 2b equals to 20. We divided this equation by 2 and we got that b equals to 20 over 2, that is 10. So we found out that b equals to 10 units, and according to this equation, b plus a equals to 16. We subtracted b from this equation and we found out that a equals to 16 minus b. But b equals to 10 units, so we substituted b by 10 and we got that a equals to 16 minus 10, that is 6. So according to the first possibility, a equals to 6 units and b, that is the hypotenuse of the right triangle ABC, equals to 10 units. That is the first option for the solution of the question, and the second solution is that b plus a is 32 and b minus a is 2. We added the two equations together, and we got that b plus b is 2b, and a minus a is 0. And 32 plus 2 is 34. So in conclusion, we found out that 2b equals to 34. We divided this equation by 2, and we got that b equals to 74, b equals to 32 over 2 is 17. So we found out that b equals to 17, and according to this equation, b plus a equals to 32. We subtracted b from this equation, and we found out that a equals to 32 minus b. We already found out that b equals to 17 units. So we substituted b by 17, and we got that a equals to 32 minus b, that is 17. So 32 minus 17 is 15. So in conclusion, we found out that according to this solution, a equals to 15 units and b equals to 17 units. Then we drew the two solutions in this page. According to the first solution, it is given us the equation that AB equals to 8 units. We just now found out that BC, that is the hypotenuse of the right, that is the perpendicular of the right triangle ABC, is 6 units, and the hypotenuse AC equals to 10 units. And inside this right triangle, we have this circle, and we want to find out the radius of this circle that is described by this specific triangle, triangle ABC. So this is the first option. Then we have the second solution. According to the second solution, we have here the right triangle ABC, side AB equals to 8 units. According to what is given as the question, we just right now found out that the perpendicular BC equals to 15 units and the hypotenuse AC equals to 17 units. And inside this right triangle, we have a circle that is described by this triangle, triangle ABC, and we want to find out the radius of this circle that is described by triangle ABC. So in order to find out the radius of this circle that is described by triangle ABC, we draw triangle ABC, a right triangle, triangle ABC that could be any triangle. In this right triangle, triangle ABC, side AB equals to A units, side BC equals to B units, and the hypotenuse AC equals to C units according to our definition. And inside this right triangle, we have this circle that is radius equals to capital R. So we will solve, we will find out the radius of this triangle, triangle ABC that could be any triangle, and then we will use the formula that we found for the radius in order to find out the radius of our specific circles that is described by those two triangles that we found out according to our solution. Okay, so we'll find out the general formula for the radius of any circle that is described by the right triangle, triangle ABC. According to this drawing, we have here O is the center of the circle, N is the point of the circle itself, therefore ON is the radius of the circle, O is the center of the circle, M is the point of the circle itself, therefore OM is also the radius of the circle that is equal to capital R. And we have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius OM. So AB is perpendicular to MO, that is to say this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. Likewise, we have the radius ON that is drawn to the point of tendency, that is to say it is drawn to point N, that is the point of tendency of tangent BC with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius NO. So if BC is perpendicular to NO, that is to say this angle equals to 90 degrees and this angle will also equal to 90 degrees according to rule number 1. So in quadrilateral MOBM, we have 1, 2, 3 right angles, and the sum of 3 right angles is 270 degrees. plus the size of the fourth angle. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, if we solve this simple equation, we found out that the missing angle, this angle MON, must be also equal to 90 degrees in order to complete the sum of the angles in the quadrilateral MOBN to 360 degrees. This angle must be equal to 90 degrees. So inside quadrilateral MOBN, we have four right angles. And any quadrilateral that has four right angles must be at least a rectangle, if not a square. And we know that the opposite sides of a rectangle are equal to each other, so here in rectangle MOBN, MO must be equal to BN. MO must be equal to BN, but we know that MO equals to R, therefore BN must be also equal to R. Likewise, according to the rule that the opposite sides of a rectangle are equal to each other, we'll get that ON equals to MB. ON equals to MB, but we have already found out that ON equals to R, which is the radius of the circle. So if ON equals to R and ON also equals to MB, it means that MB will be also equal to R. So we actually found out that quadrilateral MOBN, it is not a rectangle but a square, because all of its sides are equal to each other, they are equal to capital R. So then we found out the length of line segment AM. AM equals to AB minus MB. AB minus MB equals to AM. That is to say, AB is A and MB is R. So in conclusion, we found out that AM equals to A minus R. And here we found out also the length of line segment NC. For the dominant, it is very easy to see that NC equals to BC minus BN. Again, BC minus BN equals to NC. That is to say, NC equals to BC, that is B, minus BN, that is capital R. So in conclusion, we found out that NC equals to B minus capital R. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common start point to a circle are equal. So if you focus on the common start point, point A, from the common start point, point A, we have two tangents to this circle. We have tangent AM and tangent AZ. And according to rule number 2, they are equal to each other. This is to say, AM equals to AZ. But we have already found out that AM equals to A minus R. Therefore, AM that is equal to AZ, AZ that is equal to AM must be also equal to A minus R. So AZ equals to A minus R. Likewise, we focus on the common start point, point C. From the common start point, point C, we have two tangents to this circle, tangent CN and tangent CZ. And according to rule number 2, they must be equal to each other. So CN equals to CZ according to rule number 2. But we have already found out that CN equals to B minus R. So CZ, so here CZ equals to CN. And CN equals to B minus R. Therefore, CZ must be also equal to B minus R. Okay? So actually, if in conclusion found out that CZ equals to B minus R and AZ also equals to A minus R, and in total the hypotenuse AC equals to AZ plus ZC. Okay, the hypotenuse AC equals to AZ plus ZC. According to our definition, the hypotenuse AC equals to C, AZ equals to A minus R, and CZ equals to B minus R. So in conclusion, C equals to A minus R plus B minus R. A minus R plus B minus R equals to A plus B minus 2R. So 2R, we added 2R to this equation, and we got that 2R plus C equals to A plus B. We subtracted C from this equation. We found out that 2R equals to A plus B minus C. We divided this equation by 2, and we got that the radius that we are looking for equals to A plus B minus C over 2. So the radius of any circle that is described by a right triangle, triangle ABC, that could be any triangle, equals to A plus B, that is the sum of its perpendiculars, minus C, that is the length of the hypotenuse, over 2. Now we implemented the new formula in our drawing. Here, this is the new formula, and we implemented the new formula in our two triangles that we found out for this question. And according to new formula, capital R equals to A plus B minus C over 2. So capital R equals to A plus B. Here, A plus B is 8 plus 6, minus the hypotenuse that is 10 over 2. A plus 6 is 14, and 14 minus 2 is 4, and 4 over 2 is 2. So we found out that the first possibility for the solution of this question is the radius of the circle that is described by triangle ABC equals to 2 units. And according to the first solution, the radius equals to A plus B, that is 8 plus 15, minus the hypotenuse, that is 17 over 2. So 8 plus 15 is 23, and 23 minus 17 is 6, and 6 over 2 is 3. So according to the second solution, the radius of this circle that is described by the right triangle ABC equals to 3 units. So in conclusion, we found out that we have two solutions to the question. The radius of the circle that is described by the right triangle, triangle ABC, could be equal to 2 units or to 3 units. Okay, we finished with the first question. Then I presented to you the second question, and we solved the second question in two different methods. So here we have a quarter circle, side OB equals to 2 units, AD equals to DO. Inside the quarter circle we have the right triangle, the right blue triangle, triangle OCB. And we want to find out the area of this right blue triangle, triangle OCB. So first of all, we have here a quarter circle, therefore this angle equals 90 degrees, and AO equals to OB. Both of them are the eye of the quarter circle that is equal to 2 units according to what is given as the question. So here AO plus OD equals to, here AD plus DO equals to AO. Repeat again, AD plus DO equals to AO, that is also equals to OB, that is the radius of the quarter circle that is equal to 2 units. We defined AD as x, then DO must be also equal to x because they are equal to each other. So x plus x equals to AO, that is 2. So x plus x is 2x, so 2x equals to 2. We divided this equation by 2 and we found out that x equals to 1 unit. Here x equals to 1 unit, so AD equals to 1 unit and DO also equals to 1 unit. Okay, then we completed the quarter circle to a circle, and when we extended side CD by a straight line until it touches the circle at any point. Suppose that it touches the circle at point X. So we have here, we created peripheral angle that is BCX, but it is given us in the question that peripheral angle BCX equals to 90 degrees. But we know, we have the rule that any peripheral angle that equals to 90 degrees must rest on the diameter of the circle. That is to say, peripheral angle BCX that is equal to 90 degrees must rest on PB. That is to say, CD, when you extend CD, it must touch point P. Okay, so that is to say, peripheral angle BCX must be equal to peripheral angle BCP. Okay? Because any peripheral angle that is equal to 90 degrees must rest on the diameter of the circle that is BP. Therefore, when we extend CD, it must touch point P. Therefore, peripheral angle BCP equals to peripheral angle BCX. And here we have the right triangle, triangle POD. According to the Pythagoras theorem, we have here PO equals to 2, DO equals to 1, so the hypotenuse will be equal to square root of 5 units. The same thing is true in the right triangle DOB. This side equals to 1 unit, this side equals to 2 units, so the hypotenuse must be equal to square root of 5 units. Then we extended 9 segments AO. Here P is the O is the center of the circle, P is the point of the circle itself, therefore PO is the radius of the circle that is 2 units. We extended AO until it touches the circle point Z. O is the point in the center of the circle, PZ is the point of the circle itself, therefore OZ is also the radius of this circle that is equal to 2 units. Okay, then we presented to rule number 1 and we implemented rule number 1 in our drawing. According to rule number 1, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. In our drawing, we have chord AZ that intersects with chord PC at point O, therefore AD times DZ equals to PD times DC. AD times DZ equals to PD times DC according to rule number 1. AD equals to 1, DZ equals to 3, PD equals to square root of 5 units, and DC is the missing 9 segments, so here we got that 3 equals to square root of 5 times DC. We divided this equation by square root of 5 and found out that DC equals to 3 over square root of 5 units. Okay, then we implemented the Pythagoras theorem on the right both triangle DCB. According to the Pythagoras theorem on the right both triangle DCB, dB square equals to DC square plus CB square. dB is square root of 5, so dB square is 5. DC is 3 over square root of 5, so DC square is 9 over 5 plus CB square. We subtracted 9 over 5 and we got that 5 minus 9 over 5 equals to CB square. We multiplied this equation by 5 by 5 and then we divided by 5 in order to have a common factor with this expression. So we got that 25 minus 9 over 5 equals to CB square. 25 minus 9 is 16, so we got that CB square equals to 16 over 5. We took out all of this equation and found out that CB equals to 4 over square root of 5. Then the area of triangle DCB equals to the base of the triangle that is DC times the I to the base that is CB over 2. DC times CB over 2. DC is 3 over square root of 5 units. CB is 4 over square root of 5, all divided by 2. 3 times 4 is 12, and square root of 5 times square root of 5 is 5 times 2. 12 over 2 is 6, so it is 6 over 5. So the area of the blue right triangle DCB equals to either 6 over 5 units, so in terms of numbers, it is equal to 1.2 square units. We finished with the first method, and I presented to you the second method. So in the first method we found out that this angle equals to 90 degrees, AD equals to 1, OD equals to 1, and here we completed the quarter circle to a semicircle, and the angle PCB equals to 90 degrees, therefore it must rest on the diameter that is PB. Therefore, when you extend CD, it must touch point P. We already found out that this angle equals 90 degrees. The hypotenuse here is square root of 5, and the hypotenuse DB here is square root of 5 also. PO equals to OB, it is the radius of the circle, this is 2 units. So in the right triangle ADO, we have this angle is theta, this angle is 90 degrees, therefore this angle must be equal to 90 degrees minus theta. The same thing is true in the right triangle PCB, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Then we prove that the right triangle POD is similar to the right triangle PCB. Why? Those two angles are equal to each other, they are equal to 90 degrees. Those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. This angle is a common angle that belongs to both triangles, so this angle equals to itself. So we found out that all the angles of triangle ADO can go into all the angles of triangle PCB, therefore those two triangles are similar to each other according to angle similarity rule. Okay, and from the fact that those two triangles are similar to each other, we conclude that PD over PB equals to DC over CB equals to PO over PC. PD is equal to 5, PB is 4, DO is 1, and CB is the missing line segment. PO is 2, and PC is equal to 5 plus DC. We created the first equation, is equal to 5 over 4 equals to 1 over CB. Because multiplied this equation and found out that square root of 5 times CB equals to 4. We divided this equation by square root of 5 and found out that CB equals to 4 over square root of 5 units. Then we created the second equation, square root of 5 over 4 equals to 2 over square root of 5 plus DC. This is the second equation. Because multiplying this equation and found out that square root of 5 times square root of 5 plus DC equals to 4 times 2, that is 8. We open the brackets on this side of the equation. Square root of 5 times square root of 5 is 5. And square root of 5 times DC is square root of 5 DC. We subtracted 5 from this equation and found out that square root of 5 times DC equals to 8 over 8 minus 5, that is 3. We divided this equation by square root of 5 and found out that DC equals to 3 over square root of 5 units. Here DC equals to 3 over 5 or square root of 5 units. So the area of this blue right triangle equals to the base, that is CC, times the height of the base, that is CB over 2. The area of triangle DCB equals to the base DC times the height of the base, that is CB over 2. DC equals to 3 over square root of 5 units. CB equals to 4 over square root of 5 units, all divided by 2. 3 times 4 is 12. Square root of 5 times square root of 5 is 5 times 2. 3 times 4 is 12 again, and square root of 5 times square root of 5 is 5 times 2. 12 over 2 is 6, so in the numerator we have 6, and in the numerator we left only with 5. So in conclusion, the area of the blue right triangle DCB equals to either 6 over 5 units, or in terms of numbers, it is equal to 1.2 square units. Okay, thank you very much.